In this video, I want to introduce you to a mechanism called the Aldol reaction. Aldol reaction. It's easily one of the most important mechanisms and reactions in all of organic chemistry because it's a powerful way to actually create carbon-carbon bonds. And it'll actually be a little bit of a review of what we saw with enol and the enolate ions and the keto-enol tautorism. I have trouble saying that. Anyway, let's start with a couple of aldehydes. And just for convenience, I'll make them identical. So let's say that this is one of the aldehydes. It just has a carbon chain there. That's what the R is. It could be of any length. Who knows what's there? And then I have another carbon here. And then this is bound to the carbonyl group. And we're going to make it an aldehyde. Although you could do this reaction with a ketone as well. And just to make things clear, this carbon right here, which is going to be involved in a lot of the business here, let me draw its hydrogens. Normally, we don't have to draw its hydrogens. And just as a bit of review, the carbon that is next to the carbonyl carbon is called an alpha carbon. If this was a ketone, this would have also been an alpha carbon if this was a carbon. And we're going to see in this reaction, besides just exploring the reaction, is that these hydrogens are actually much more acidic than traditional hydrogens attached to carbons on the rest of the chain. And it comes from the fact that this proton can be given to something else. The electron can go to that carbon, and then it'll be resonance stabilized. And we're going to see that in a second. Now, I said I would draw two molecules of that because we need two molecules. We're actually going to be, to some degree, joining the two molecules. So let me draw another aldehyde right over here. And I'm going to draw it symmetric to this because it'll make it, I think, a little bit easier to visualize the two molecules. Actually, let me just draw it the same way. But I'll draw it in a different color. So you have the R group, and then you have the oxygen right there. And I won't draw all of the hydrogens on this guy. But this and this are the exact same molecule. It's just the hydrogens are implicit here. Now, the aldol reaction I'll show you will be in a basic environment. So you can imagine that it'll be catalyzed by a base. And so imagine we have some hydroxide laying around, some of the hydroxide anion. Hydroxide, let me do that in a different color. So let's say we have some hydroxide anion floating around, negative charge, just like that. I just told you that these hydrogens are much more acidic than hydrogens anywhere else on a carbon chain, these alpha hydrogens. So you could imagine a situation where an electron from the hydroxide is given to one of these hydrogen protons, and then the electron that was associated with that hydrogen is now given back to this alpha carbon. And so if that were to happen, the next step in our reaction would look like this. And I'll draw it in equilibrium. Actually, let me draw it this way. So the next step in the products of that step, we'd be in equilibrium with, you have your carbon chain, or the rest of your molecule right there. And that's just to show that it could be anything. It's attached here to the alpha carbon, which is now going to be negative. I'll show that in a second, which is attached to the carbonyl group, which is attached to a hydrogen. And actually, I'll stop drawing that hydrogen for now, too. Just we know it's there. But I'll keep drawing this hydrogen right over here. The other hydrogen was taken away, and this alpha carbon now has a negative charge because it got the electron from that proton. And of course, we have the hydroxide grabbed this hydrogen, and it is now water. Now, the reason why this was acidic to begin with is because this is resonance stabilized. And I'll show you that it's resonance stabilized right now. This alpha carbon right here can give its electron to the carbonyl carbon. And if the carbonyl carbon gets an electron, it can give an electron to this oxygen up here. It'll break the double bond. So this configuration is resonance stabilized with this. So I could draw it like this. You have your R, and then you have a single bond to this oxygen. It now gained an electron. It is now negative, and you now have a double bond just like that. And I could draw this hydrogen if I like, or I don't have to. It's implicitly over there now. And you might be familiar with this. This is the enolate anion. This right here is the enolate. This This is the enolate ion. If we had a hydrogen right here, it would be an enol. And we would say, hey, this is the keto form. This is the enol form. We've seen this before. Now, what's interesting about the enolate ion is it can act as a nucleophile. It can do a nucleophilic attack on the other aldehyde's carbonyl group. But it does it in kind of a non-conventional way. And I'll show you how it does it right now. So it does the attack like this. So let me draw this guy over here. So you have the carbonyl group, and then you have its alpha carbon, and then you have an R group right over there. There's actually a hydrogen right over here as well. I just flipped it over. This and this are the same molecule. And let me make it clear. These two guys right here are resonance forms. And this is, once again, this is the reason why it's easier to take this hydrogen than other hydrogens on a traditional carbon chain. Easier to take an alpha hydrogen to a carbonyl group because you have this resonance structure. But this enolate ion, especially this configuration of it, you can imagine it doing something like this. You can imagine this oxygen giving back the electron to the carbonyl carbon, to this carbon right here. And when that happens, then this guy is going to be giving up. He's going to be giving up an electron. And that electron that he gives up, let me do it in a new color. This electron that he gives up could go and do a nucleophilic attack on this carbonyl group. And so if that carbonyl carbon gets, let me do this in a new color. If this carbonyl carbon gets an electron, then it could give away an electron to that oxygen right up there. So the next step after this, we would have something like this. And once again, I'll show it as happening in equilibrium. So from here, we go right over there. And what we have is a situation where, let me draw this guy on the left first. So we have a double bond to this oxygen. Now, actually, let me draw the second. So this is this oxygen. We now have a double bond. And let me do it in this same purple color right over here. And then we have the rest of what was an aldehyde. Where you have, let me do that in that same color. And then you have your R group right over there. But now this electron get an attack on this other aldehyde. So this guy right here, this alpha carbon, it's that same alpha carbon we've been dealing with. The same alpha carbon is now bonded to this carbonyl carbon. So it is now bound to this carbonyl carbon right over here. And so it will look like this. It will look like, let me draw it with the right colors. Get the orange out. So that carbonyl carbon, it now has a single bond to this oxygen. This electron was taken back by it. So this oxygen now has a negative charge. And it is bound to its alpha carbon. And then that is bonded to another group, probably a chain of a carbon chain or something that contains a carbon chain, another functional group, whatever you want to call it. And then the final step, this anion can get rid of its negative charge by essentially grabbing a hydrogen from maybe from this water that was formed before. Obviously not going to be the same molecule, but it could grab it from this in a previous step, this water molecule that was formed in a previous step. And of course, this is all in a basic environment. So it can give an electron to this hydrogen, and then the hydrogen proton would lose an electron to the hydroxide, and the hydroxide will become negative again. And so what will be the final product? The final product will be and I'm just going to try my best to redraw this thing right over here. You have this part of the molecule. So you have this carbonyl group right over here. It is attached to this radical group right over there. So that is this part. And I can even do the same colors. This bond right over here is this bond right over here. And then this carbon is attached to a carbon that's attached to a hydroxyl group now. So it'll look like this. And let me draw it. So this oxygen is now this oxygen. And it just captured this hydrogen. So it is now a hydroxyl group. It's now an OH. It is now an OH group. And then finally, this guy is bound to what was an alpha carbon. It's not anymore. what was an alpha carbon, which is then bound to a radical group. And if we want, we can remember that there was always, from the get-go, there was always a hydrogen over here. So why is this called the Aldol reaction? Why does it matter? Well, it's called the Aldol reaction because what we formed is both an aldehyde. Notice this is an aldehyde, and it's an alcohol. So that's where the word aldol comes from. But the more important thing about this, and I don't want to mislead you. You could have also have done this with a ketone. You could have had a methyl group or an ethyl group. You could have had a big carbon chain here. It still would have worked. So the aldol reaction doesn't only form things that are aldehydes and alcohols. It could have formed something that's both a ketone and an alcohol. But that's why it's called the aldol reaction. But the more important thing about the aldol reaction is, one, it shows you how the enolate ion can be a nucleophile. It shows you why the alpha hydrogens are more acidic than hydrogens on other parts of carbon chains. But the most useful aspect of it is it's a useful way to actually join two carbon chains together. Notice we were able to join this alpha carbon right here to this carbonyl carbon over here to form this aldol. Or sometimes this will be called, because this is still an alpha carbon right here. This is an alpha carbon. This is a beta carbon. And so this will be referred to as a beta hydroxy. And we've probably used things from the pharmacy that has this word in it. This is also called a beta hydroxy. This is alpha, this is beta. It has a hydroxyl group on the beta carbon. Beta hydroxy aldehyde. Beta hydroxy aldehyde. Anyway, hopefully you found that entertaining.